So now we consider the mechanism of the Dotz reaction. This is a little more complex, so you have to look at it a bit carefully. I have on the product side the introduction of two carbons. You have an alkyne and you have a carbene. So that takes care of 4 carbons, and the second 2 carbons that are coming in, one is coming in actually from the introduction of carbon monoxide. So let us write it in such a way that the most reactive components in the reaction mixture will react with each other. The carbene is the most reactive form, and you have an alkyne. The two can react as if they are going to undergo metathesis. I have drawn that for you in this slide, and in fact I have drawn it in such a way that you can see the interaction of the alkyne with the chromium carbon double bond through the formation of, let's say, 2 new bonds, a carbon-carbon bond, which is labeled now as, which is shown as dotted bonds, and a chromium carbon bond, which is also shown as dotted bonds, and it will result in the 2 bonds that are shown in structure A, which is in fact a metallocyclobutene. The metallocyclobutene is a strained ring system, and it will only have a fleeting existence, but because I have these carbon monoxides attached to the chromium, I can now have a simple CO insertion reaction, the migratory insertion reaction of the vinyl chromium carbon bond to the CO, and that will give me a metallocyclopentenone. Notice here that I have separated out one carbon monoxide on the chromium in violet color, so you can see the difference between the different carbon monoxides which are present. One is now inserted into the ring system, so you have a metallocyclopentenone. If I make this molecule undergo reductive elimination, I will have a bond formed between carbon atom number 1 and the carbon monoxide which just came into the ring, which is marked in violet. That will give me a very strained 4-membered ring. Instead, I can undergo a migration reaction. Now, it turns out that you can have one more carbon monoxide migration reaction. In that case, the product will have 2 COs adjacent to each other. Apparently, that is not happening. Instead, the chromium carbon bond, which is labeled as CRC1 bond, which is present in this intermediate B, that intermediate undergoes a 1,3 migration reaction in which the chromium carbon bond migrates from position 1 to position 3. So you could have migrated the second carbon bond which is attached to carbon atom number 1, which is attached to the R group, but then that is a very strong bond. So the weak bond, the chromium C1 bond, which is a weak bond, that migrates to carbon atom number 3 in the aromatic ring system. That gives you intermediate C. That gives you intermediate C, which looks a bit weird because we have not been able to draw it in 2 dimensions. But it is a perfectly stable ring system that would be formed by migration of the chromium carbon bond from this position which is there to the new carbon atom. Instead of C1, it is being attached to C3. So this will give you the intermediate C, which can undergo reductive elimination. what I have done is I have drawn another form of C so that you can see how this intermediate is not so strained after all. It's a perfect metallocycloheptatriene, in fact. Okay, so you do have a nice intermediate C formed, which can extrude CrCO4, which can undergo reductive elimination in order to give you the product. It doesn't quite look like the product because this is the keto form of the enol, which is the actual product. And so I'm going to draw an arrow to indicate the fact that you do have a enol form which is actually coordinated to CrCO3, which might be formed at the end of the reaction. So you have a hydrogen migration from the third position on to the CO. That will give you the product.